A URL shortener looks simple. Give it a long address and it returns a small code such as X7KP2AQ. But now imagine storing 10 billion links. At peak traffic, people open 100,000 short links every second. Most of the work is reading an existing mapping, not creating a new one. The redirect service should answer in less than 5 milliseconds before normal internet travel time. That target rules out slow coordination on the red path. So we will separate 3 paths. First, the create path produces a unique code and saves its mapping safely. Later, the redirect path receives that code in a new browser request, finds the long address, and returns immediately. Only after the response is sent does the analytics path process a click event. Analytics never blocks the user. Start with the design contract, 10 billion stored links. Peak redirect traffic is 100,000 reads per second. New links arrive at about 1,000 writes per second. That is roughly 100 reads for every write, so caching deserves more attention than write throughput. The internal redirect target is under 5 milliseconds. The create path can take longer because it is not on every click. These are assumptions, not facts. In an interview, confirm link lifetime, custom aliases, edits, geographic traffic, availability, abuse controls, and whether the latency target includes the public internet. Every architecture decision should point back to one of these requirements. Now, create one short link. We need a compact code that stays unique while many generator nodes create links in several regions. Instead of contacting one central service for every link, a small ID allocator occasionally leases a non-overlapping range to each regional ID generator node. Engineers often call this reserved range a block. For example, one generator in region A receives the range from 1,250,000 to 1,259,999. No other generator receives those numbers. The allocator is involved only when that generator needs another range. It is not called for every new short link. The normal request now stays local. The generator advances a node local atomic counter and takes the next unused number from its own lease. For this request, that number is 1,250,904. This is all consume means here. Take one unused ID and advance the local counter so the node cannot issue it again. There is no global request time lock because this generator alone owns the range. After an uncertain restart, it must resume from durable progress or abandon the unused remainder rather than risk reusing an ID. The number is unique, but a simple sequence is still predictable. It leaks business volume and makes nearby links easy to guess. A keyed reversible Feistel permutation shuffles a fixed width numeric domain. Because it is a permutation, two different inputs in that domain cannot become the same output. We encode the entire shuffled value with base 62 digits, lowercase letters, and uppercase letters. We do not truncate it because truncation could reintroduce collisions. The result is a short code such as X7KP2AQ. The service writes code, long URL, owner, and status to the durable mapping store. Only after that write succeeds do we return the short link. Non-overlapping generator leases guarantee uniqueness. Feistel hides the sequence. Base 62 makes the result compact. Now somebody opens that code. One request must discover the long URL and return an HTTP redirect. First, a content delivery network near the user checks its edge cache. A popular immutable redirect may finish here. Editable or disableable links need a bounded edge TTL or explicit invalidation, so the edge cannot serve stale policy forever. On an edge miss, the redirect service checks a small in-process least recently used cache. This is the fastest application lookup, but every process owns a separate copy. Next comes the shared Valky cluster. It stores a much larger hot set and absorbs most remaining reads. Valky is an acceleration layer, not the source of truth. Only a cache miss reaches ScyllaDB, the durable mapping store. We query one row by shortcode, then refill each cache with the product's freshness policy. The service returns HTTP 302 with the original address in the location header. 302 lets later requests observe a changed or disabled mapping once the cache policy refreshes it. A permanent, immutable product could evaluate 301 separately. Why does this cache hierarchy work? Link traffic is usually heavy-tailed. A small number of links receive most clicks, while billions of links are rarely opened. For planning, suppose the hottest 1% of links produces 80% of reads. A cache much smaller than the full link corpus can then absorb most requests because it stores the popular mappings rather than every mapping. Out of 100 requests, 80 finish in the hot cache and only 20 continue toward colder storage. This is an assumption behind the design, not a guaranteed hit rate. If traffic becomes uniform, the same cache covers far less useful traffic. Misses rise and database load rises with them. Measure the real popularity curve, cache hit rate, eviction rate, and database reads. Capacity plans must change when the traffic shape changes. A heavy-tailed workload also creates hotkeys. Imagine one celebrity link suddenly receiving 100,000 requests per second. Hashing by code sends every database miss for that link to the same shard. If the shard safely handles 50,000 reads per second, one key can overload it while the rest of the cluster stays quiet. The first shield is the in-process cache. Every redirect pod can answer the viral code from memory, spreading reads across the application fleet. The second shield is expiry jitter. Cache copies expire at slightly different times, so they do not stampede the database together. The third shield is request coalescing, also called single flight. Within each process, one miss refreshes the key, while concurrent requests wait for that result. It does not coordinate different pods unless we add a distributed mechanism. For an exceptional key, extra read replicas or a dedicated distribution path provide more physical targets. These protections should activate from measured traffic with limits and back pressure. A viral or abusive link should not require an operator to redesign the system during the spike. Now assemble the system as 3 separate lanes. The read lane is latency critical: edge cache, redirect service, local cache, Valky, and ScyllaDB. It stops at the first hit and returns the redirect. The right lane leases an identifier, permutes it, base 62 encodes it, and stores the mapping durably. After the database confirms the write, the service may populate Valky. If links can change or be deleted, updates need explicit cache invalidation or versioned entries. The analytics lane begins only after the redirect response. The service publishes a compact click event to Kafka. Consumers can enrich it and write aggregates to ClickHouse without blocking the user. If Kafka is unhealthy, redirects continue. We may buffer a bounded number of events or drop low priority analytics with a metric, but we do not wait for a dashboard. That separation is the architecture. Durable mappings are truth, caches accelerate reads, and background analytics remains outside the redirect's availability path. Now test the design. If Valky disappears, ScyllaDB still owns every mapping and the service can rebuild the cache. Replicate durable data across failure domains and route users to healthy application capacity. Multi-region writes still need an explicit ownership or conflict strategy. Rate limits, malware checks, reserved aliases, and link disable controls protect the product from abuse. These checks belong mainly on creation and administration, not on every redirect. Monitor redirect latency by tier, cache hit rate, hotkeys, shard load, error rate, and analytics drops. The design is not one fixed answer. A smaller product may use one relational database and one cache. The important part is preserving the same boundaries as scale grows. A strong interview answer starts with the workload and product rules, not a list of databases. Then separate, create, redirect, and analytics paths. Explain the data moving through each path and where it becomes durable. State assumptions behind numbers such as an 80% hit rate. Name the Zipf-like traffic shape and say that production measurements must confirm it. For every acceleration layer, name the fallback. For every asynchronous dependency, explain why user traffic survives its failure. Finally, name trade-offs. UUIDs may be operationally simple but produce longer codes. Counters are compact but need allocation. 301 caches strongly, 302 preserves control. That reasoning is more valuable than one fashionable stack. Remember the right path, lease a unique number, hide the sequence, encode it compactly, and store the mapping durably. Remember the read path, edge, local cache, shared cache, then the durable database, followed by a fast redirect. Remember the traffic shape, a small hot set makes caching powerful, and a viral key needs automatic protection. And keep analytics asynchronous so reporting can fail without breaking redirects. That is the URL shortener mental model. Find deeper engineering guides and role-specific career paths at crackingwalnuts.com. Follow Cracking Walnuts for the next visual breakdown.